Well, good afternoon and good evening, everyone. Welcome at the Institute of Theoretical Physics, located at Paris-Saclay. So a number of research fields are studied here in our institute, from statistical and condensed matter to cosmology, particle and mathematical physics. And we are interested in how quantum technology, in particular quantum computing and simulation, could help to solve long-standing problems in some of these research fields. So with the financial support from a European project called the Quantum Internet Alliance, we took the initiative to organize this series of conferences to try to answer this question. So this is a series consisting of 5 conferences given by renowned researchers having both a clear understanding and of the efforts that are currently ongoing, and also a long-term vision going along these lines. So we are now having our second talk in this series, and it will be given by our speaker of tonight, Professor R.Laflamme. So he was, just to introduce him very briefly, originally from Quebec, and he did his PhD on quantum gravity and cosmology at the University of Cambridge in the UK, under the supervision of Stephen Hawking. Then his interest shifted to quantum computing, where he made very significant contributions, including laying down the mathematical framework for quantum error correction, and also proposing ideas for linear optical quantum computing, which could be seen as a precursor of measurement-based quantum computing. Professor Laflamme is a founder of the Institute for Quantum Computing in Canada, which he directed for 15 years. He received too many awards and distinction to be mentioned here. Today, Professor Laflamme is a professor of physics and astronomy at the University of Waterloo in Canada, and he's also the John Farneman Chair in Quantum Information at the Institute of Quantum Computing. So for all these reasons, it is a real delight to have you with us, Ray, today. And many thanks for accepting our invitation. So for the audience, don't hesitate to ask questions on the chat if you are online, or you can keep your questions for the end of the presentation if you are in the room. We will have a time of questions after the presentation of the speaker, and I will be reading the questions which are on the chat. With this, that's all I have to say. So the floor is yours, Ray.
Thank you very much, Pierre Francesco, and thank you to Nicolas and Jean Daniel for having invited me, and Jean Daniel in particular, who was a summer student of mine some years ago and made the first contact. So it's a great pleasure to be part amongst you today, even if it's through these video links, and hopefully in the next couple of months or years, we can start again to be face-to-face. So it's my first time that I use this big blue button Zoom video conferencing system. So if there's something that doesn't work, don't be shy to kind of give me a shout. And I use a PowerPoint presentation, which will turn my windows into the windows of the presentation. So I will not see the public chat. So if you have a question, shout to me or let Pierre Francisco kind of tell it. And I'm very happy to entertain a question as we go through. So let's start with this. So I assume you do see that first slide. So I've been working in quantum information for the last probably around 25 years and did work on error correction and on linear optics, but also despite the fact that I was trained as a theoretical physicist, I got really interested in experiments some years ago, and I did experiments related to nuclear magnetic resonance. And the main interest that I've had in there was to test some of the ideas of quantum error correction. But that's not what I'm going to talk about today. I'll mention a little bit about NMR and error correction, of course. But what I would like to do is to talk about the different implementation for quantum computers. So I assume that there are many of you who are not specialists in quantum computing, and then if you are, then you probably know quite a lot about what I'm going to say. So I assume that there's a bunch of you who are kind of learning about quantum information, and this is what I'm going to talk about. But before I go there, I want to mention a little bit about what we've been doing in Waterloo in the last 20 years since I moved there in 2001. We've built, or we are building, a quantum system. The idea of kind of having a bunch of different institute organizations who are working together to go from the fundamental science of quantum information to its commercialization. And there's a few elements of this. The Perimeter Institute is one of them. The Institute of Quantum Computing, who kind of has both theoretical and experimental work in quantum information, mostly dealing with fundamentals ideas or fundamental research in quantum information. But in the last few years, we've had what is called the Quantum Valley Ideas Lab, which is really a prototyping and commercializing lab. And to kind of bring all of this together, Quantum Valley Investments as venture capital funds that helps kind of turning the ideas into potentially social impact, to promote the social impact of quantum information. So despite being a theoretical physicist by training, I've learned a lot of different things in my last 20 years, both from the experimental side, the theoretical side, but also the idea of bringing quantum information science in a broader context. Okay, enough for this. Let's go and talk about what my talk is going to be about. First, a few elements about a brief introduction in case you don't know too much about quantum information. Some elements of to build quantum computers, and I'm going to talk about 4 technologies. NMR as an introduction and just to set the scene and talk about different pieces that a quantum computer needs. But these 3 optics, ion trap, superconducting device are probably kind of the horses that are further ahead in trying to build quantum computers. I nearly thought about bringing quantum dots or something like topological qubits also, although in 45 minutes it's hard to talk with enough details in talking about too many things. So I am going to focus only on these 4 devices. And then I will finish by talking a little bit about once we have devices, how do we benchmark them? Are we interested in comparing them and assessing how good they are, in particular their control? I should point out also that this you will see in probably the next 6 months to a year, I'm writing a book with some of my colleagues here at the University of Quantum Computing on elements to build quantum computers, in particular the experimental part, and trying to kind of bring these different technology with the same framework of quantum information and explain how they work. And this came out of some courses that I've been teaching collaboratively with my colleagues, both at the graduate and, interestingly, on the undergraduate level. So let's have a very brief history of quantum computation, and there's definitely starting points that people can come from to see how quantum information is developed. But the one that I like to emphasize the most is to start with Moore's law and the expression of the shrinking of transistors as time goes for practical and financial reason to make classical computers more powerful. And in the early 1960s, Rolf Landauer was thinking about the impact of this, of having shrinking transistors. And one of them is the limitation that this would happen if we have devices which are doing non-reversible computation, like what we see with classical computers and transistors. And the challenge is that every time that we have an operation which is not reversible, then we will have to erase some bits of information, and there'll be a challenge with the heat extraction. And one naive way of thinking about this is if you're doing always the same computation and you're shrinking the size of your chip, then at some point the fan that needs to be there to extract all this heat will be limited as the kind of surface area is going to decrease. Then at some point you'll have melting down of your classical chip. And in order to kind of resolve that problem, Charlie Bennett, who was also at IBM, started to think about, could we have a reversible computers? And in particular, he was thinking about, instead of erasing bits, the way that Landauer was thinking of, can we do this in an efficient way? There's a naive way of doing it, just discarding bit, but keeping them in memory somewhere so that you don't have to erase them. But this naive way of thinking would take an exponential number of these extra bits, which was not kind of a reasonable way. And what Bennett found was a way of doing this in a reversible way. And starting from this, Paul Benioff started to think about what kind of theory that we have which are reversible. And definitely quantum mechanics is one of them. And he showed how we can manipulate Hamiltonians of quantum system in order to be doing reversible quantum computation, reversible computation. And at the time, he didn't realize that to bring quantum mechanics in the world of computation would allow something which would be fundamentally interesting. And it is Feynman who realized this, that there were computation, simulation of quantum system, for example, that could be a lot more efficient if we use a quantum machine instead of a classical machine. And so building from this, then people started to think about algorithm that would be more powerful with quantum computers than classical computers. So David Deutsch, Richard Giosa started to think about ways of manipulating this. And one kind of breakthrough that happens around the early 1990s, in 1994, Peter Shor realized that it was possible to factor numbers which are product of prime using a quantum computer instead of a classical one. And that problem was very much of interest broadly, in particular by the NSA, because today's encryption is based on factoring numbers which are product of prime, or the security is based on the challenge or the difficulty of doing this on classical computer. And so this really brought a boost, certainly in the US, of funding of trying to investigate this. But there were quite a lot of people were pretty skeptical about this being possible. And there was a famous paper by one of your colleagues in Paris, Serge Haroche and Jean-Michel Raymond, who talked about quantum computing. Was it a dream or a nightmare? And at the time, ideas of quantum error correction had not been discovered. And I'll mention a little bit more about this in a few minutes. But another part which was interesting in the mid-1990s is the development of, or the proposal of some technologies, and in particular optics, ion trap, NMR, and superconducting junction were proposed, but at a very, very naive level at that point, as very few experiments were done, and the first demonstration of manipulating 1 or 2 qubits were done roughly at that time. I think if we go now to the 2010s, most of the impact has been in increasing the control of qubits, making it more precise, without increasing the number of qubits dramatically, certainly up to 2010s, developing new algorithms and thinking about different applications that people have been doing. And things have kind of started to change quite a lot in the 2010s, where there's been an interest from industry, and so some kind of focus of turning kind of device, which was really proof of principle, into something which kind of could be useful. And we are kind of pretty much in this era right now, the era of NISQ, which is kind of a short abbreviation for noisy intermediate scale quantum computers. Are computers, quantum computers, where we have a sufficient number of quantum bits, which becomes really hard to simulate on a classical computer, but not yet there to be able to implement quantum error correction. Few little things that you might know or might not. The notion of qubit is typically a two-level system, with a system with two levels, which we'll call 0 and we'll call 1, or in a mixed state defined by the state rho. It is manipulated by unitary transformation, which is a shorthand to say the algorithm that we want to do, and we do some measurement at the end. And putting all of this together, we get the notion of quantum circuit, which is kind of a language which was created pretty much by the quantum computer scientists, which had been kind of followed what we've seen in classical computers, the idea that we have an initial state, and then we have our qubits, which are little lines in here, and then a set of gates. We have the so-called 1 qubit gates, which manipulate 1 qubit one at a time, and we have kind of two sets of a gate which manipulates a set of 2 qubits. For example, this little symbol here corresponds to a control NOT, and a control NOT is a gate which flips this bit here, the target, once the control bit is 1, doesn't do anything when it is in the state 0. And it turns out that these becomes a universal set of gates, the 1 qubit gates, and one type of 2 qubit gates. So we will see this a little bit during this talk. So if you haven't seen this before, it is in fact a very useful tool, especially when you talk about different technologies, because at the end they do the same things. These technologies is trying to implement these kind of algorithm. By the way, this algorithm here is one for doing quantum error correction for a very simple type of noise, phase type of noise, which kind of was implemented some years ago in an MR by myself and some of my colleagues. A second thing to remember quite well is quantum complexity, which is, again, a quantum version of classical complexity theory, which assess a difficulty to solve certain types of problems. And very naively, certainly seen from a physicist, there's two types of problem that exist, the hard one and the easy one, at least in the computer science language. The hard one are those that takes an exponential number of resources in terms of their input, and the ones which are easy takes a polynomial amount of resources, or the so-called P problem. The problem which are hard from a classical point of view are called NP, and there's a subclass of them which are NP complete. And it is believed that quantum computers are in this class called BQP, which can do some things that is hard for classical computers, but cannot solve all NP problems. So if you've heard that somewhere that kind of quantum computers can solve NP problems, then it is not something that we certainly know at present. So there's some hard problems that can be solved, but not all the hard problems for classical computers. Okay, now let's go back and talk about building quantum computers. And there's a set of criteria called the De Vincenzo criteria that are being used to do this. And when I talk about different proposals, I will go through all of them one by one and explain very briefly how they are implemented. So first, we have to have a physical system and a well-characterized qubit. So qubit, again, are physical system. We have 2 states, 0 and 1, or maybe to be slightly more precise, they are systems whose observable are the Pauli matrices, which kind of is slightly more general definition of a qubit. And we want them to be scalable in the sense that if we have 1 qubit and 2 qubit, and we want to add a third one or fourth one or an nth one, the amount of resources to do this, and by resources here is this, how much does it cost you in your lab, as an example of that, then doesn't go up exponentially. we need to be able to take these qubits and to initialize them in a particular state. We'll call this the state of all zeros, for example, but could be any kind of states. And typically it is a pure state that we're interested. But maybe in some simulation of quantum physics, we might want to be in some thermal state of an Hamiltonian. And so we will have to be able to kind of reach that thermal state in some efficient way. The third piece is related to control. And on a classical computer, you would have a transistor, and it's totally amazing that with only a small device called a transistor, and you put a bunch of transistors together, you can build any kind of algorithm that you want. You can implement any algorithm that you would like to. The equivalent of this for quantum computers is a set of, as I mentioned before, 1 qubit gate and a 2 qubit gate. And for example, a universal set from which we can build any unitary transformation U, for example, for 1 qubit, consists of Hadamard gate, the state which goes from 0 and 1 to the so-called plus and minus state, and T gate, which is some form of phase gates. And by combining both of them together, we can do any unitary for 1 qubit. And if we augment this by a control knot, then a unitary on n qubit can be implemented. And if we use a polynomial number of H, T, and C naught gates, then this algorithm will be called efficient. If not, it'll be an exponential number, and then it'll be an inefficient algorithm. I've put the set here. There's other sets of 1 qubit gates also that people have been using, but this one, which is mentioned here, has the property that both H and C naught gates are part which is called the Clifford group, and I'll come back to that in a few minutes. And turns out that the T gates doesn't belong to this Clifford group. We need to have a measurement capability. This is the fourth division criteria. That is, we have to be able to measure our qubits. We typically think that we're measuring in a state in the basis of 0, 1, but we can change any basis using some unitary transformation like U. And finally, we need to be able to do all of these pieces in a time which has a long relevant decoherence time, a decoherence time which is much longer than the gate operation, the time to implement either the 1 qubit or the 2 qubit gate. And you might want to ask the question of what does it mean? How much longer? Is there a term for this? And it turns out that quantum error correction provides the answer of this. And the idea of error correction came from the fact that if you have a probability of error, or probability of success for making 1 gate, which is 1 minus epsilon with the probability of error. If you make n of these gates, then this probability will go down exponentially. So if we don't have a perfect quantum computer and we have errors that we don't know how to control, then the exponential gain that quantum computation would give us would be canceled by the exponential decay of the probability of success. And that was one of the main reasons why people like Rolf Landauer and Serge Haroche didn't believe that we would be able to build a quantum computer. What they had not foreseen is quantum error correction. And I won't go into detail of quantum error correction, very interesting subject and kind of critical for quantum computation. But the most important piece is that the probability of success will not go down exponentially, but with an amount of resource which is not unreasonable, that is a polynomial amount of resource, then as long as the noise is below a threshold, and the threshold depends on what kind of code we use, what kind of error we have, what kind of technology we have, what kind of gates we have there. But typically the amount of threshold is 1 error per 100 gates to 1 error per 1,000,000 gates, depending on the code that people have. And if we reach this accuracy threshold, then we can implement error correction, and the amount of resource that we need to have a reasonable amount of probability of success at the end of an algorithm will not go down exponentially with the number of gates or number of qubits that we have. So very, to say it in simple words, is that imperfection and precisions of realistic device are not a fundamental objection to quantum computing. Now, this doesn't say that if we have errors, we automatically are able to implement error correction. This works only for some types of error that we know, but we believe that these types of error are the ones that we find in reasonable devices like the one that I'm going to mention in a few minutes. So let's first go and talk about NMR quantum computing, just as an example of a typical quantum computer. It contains a quantum processor, and the quantum processors are the nuclear spins of atoms in a little sample. We take this little sample and we put it in a special apparatus that we hold and prepare the qubits. And here, in this case, it's the magnet. The magnet has two roles. It kind of put a polarization on these qubits, prepare the initial state, and gives them a Larmor frequency, which is different from qubit to qubit, to be able to distinguish the qubits from themselves. Then we have a set of electronics, which are used to kind of control the qubit, to implement the qubit gates. And finally, we have a classical computer, which control the electronics, which control the quantum processor. So that all devices for quantum computation have pretty much the same structure as this. And so we will always have a quantum computer which is as powerful as classical computer because it includes a classical computer. There are ideas of cellular automatas or quantum cellular automatas where we might be able to kind of get rid of only the classical computer files, but I will not talk about these devices. So let's go through definitions of criteria for NMR. So the idea is to use, as I mentioned, the nuclear spins of atoms, and we look at spin half particles. And so here's a molecule that we have been interested in, and the chlorine atoms have spin 3/2, and it turns out they interact very weakly with the carbon, so we kind of can forget about them. Oxygen has spin 0, so we do not see them. So here we will have 7 carbon 13, 5 hydrogens. I count this one, and these 3 here, but not this one. I'll explain this for a second. We put this in a strong magnet, and although the carbon 13s all have the same Larmor frequency, there's electronic clouds in the molecules which shields different carbons in slightly different way, which leads to what is called a chemical shift and leads to the 7 carbon to have different Larmor frequencies. So we can identify them, and we can send RF pulse to implement our 1 qubit gate, which kind of can distinguish a pulse, let's say, on carbon 5 or on carbon 3. The 2 qubit gates are implemented through what is called a J coupling. And the J coupling is an interaction between nearby nuclei, which is induced through the electrons cloud that I just mentioned a few minutes ago. The electron cloud energy is slightly different if this carbon 6 and this carbon 7 are pointing in the same direction or in opposite direction. And so this induces a coupling between the two, and we are using these couplings. In the case of NMR, these couplings are hundreds of hertz, and these gates, the 1 qubit gates on these, can be done on a microsecond. So this is very slow, and this is one of the challenge of NMR. The state preparation is done by taking the thermal density matrix, e to the minus beta h, and then turning it into a state of the form epsilon psi. And because the measurements are the trace of one of the Pauli matrices, this term kind of never appear. So this behaves like a classical quantum states. It can be all in the state 0, and then we can do quantum computation with this. Challenge of NMR is the noise. Then we have something called T1, which is if we take a spin which is polarized in this way, we do a 180 degree to put it out of equilibrium, and we calculate the amount of time that it takes to get back to equilibrium, and this is related to T1. And if we have a density matrix, this is related to how the diagonal terms of that density matrix, how do they get back to equilibrium. There's another type of noise called T2, which is called the dephasing time. And this is observed by taking the spin and then putting it in the XY plane. The alarm frequency is going to make it rotate around and around the Z-axis, which is pointing up. As it kind of turns around, then the change of phases due to coupling with extra nuclei or inhomogeneity of the field is going to be damped. And this will tell us that the off-diagonal terms of this is going to decay, and the decay time is given to T2. So despite these times of 10 seconds and 1 second, we can do 1 qubit gates and 2 qubit gates with a precision of about 5 to 10 to the minus 3, which is kind of 1 error, half an error, and about kind of per 100 gates. Success of NMR has been that we are able to manipulate up to a dozen of quantum bits. As I mentioned, quite a good control of these gates. And also, as the system are relatively slow, the technology for pulse, to make the pulses, to make these 1 qubit gates is quite well developed, and we can shape this pulse to mitigate certain types of errors. And this kind of shaping of pulse is something that has been taken up by many other technologies. Challenge, scalability, and in particular finding larger types of molecules which have their alarm frequency between all the carbons or all the atoms being different from each other, and kind of a T2 time divided by the gate time, which is hard to improve. So there's very little things that we can do to make to increase the precision of the gates that we do. Pulse shaping has been quite an impact, but once you've done this, there is no other way. And in other technologies, it is possible to do this. Finding larger molecule moving to a solid state or electron spin resonance is one way, but it turns out to be quite a challenge to be able to manipulate larger type of system, even of 12 qubits using solid state or ESR. Interestingly, there's a few companies who make little devices, a company from China, one from New Zealand, one from Europe, Bruker, who made little prototypes of these quantum computers, which are good for teaching. And in fact, in the classes that I have had, I have students going and play with these qubits and develop their intuition of quantum computation. A different technology that I'm going to talk about now, move on to the second one, is optical quantum computing. And in that case, the qubits are photons. And there's different degrees of freedom that can be used. We can make single photons and use them in what is called the dual rail encoding, where we take, in fact, 2 modes of photons, 2 spatial modes. We can think about here and here as being 2 optical fibers or 2 waveguides in a chip. If the photon is in the first mode, we'll call this the 1 state of our qubits. If it is in the second mode here, we'll call this the 0 of the qubits. So in that particular case, the kind of quantum information space is different than the physical space of the physical system that we're manipulating. And so we have to take this into account. And very interestingly, other ways of doing this, we could have used the parallelization of the photons as 1 degree of freedom, or using continuous variables. And there are application of these 3 types of degrees of freedom in different technologies for optics. If we use single photons, the challenge for state preparation is to prepare very good single photon, to have very single photon sources. And there is a single photon sources which are in demand. That is, we push a button and a photon comes in. It has to come in with a waveform so that the second photon has a very, very similar waveform so that they can interfere with each other as we do the quantum computation. How do we control them? Turns out that in this particular encoding, the dual rail encoding, relatively easy to do a 1 qubit gate. If we put a little phase shifter in here, this phase shifter is going to induce a Z rotation in this block sphere that I mentioned in the previous slide. And the X or the Y rotation can be implemented with a beam splitter between these two modes, and depending on the characteristic of the beam splitter, it will correspond to a different Y or X rotation. And if we combine a generic Y rotation with a generic Z rotation, this becomes a universal set of quantum gates for 1 qubit. What is challenging in optics is the 2-qubit gate. And the reason for this is that photons don't interact much with each other. The interaction is very, very weak. And really a control knot is a gate which tells you that if you have a photon in a certain mode, then it does something different to the other mode. And so the photon being there or not has to control a second mode or a second qubit. And this is really kind of an interaction which is kind of a nonlinear process. And so very hard to do. And people have tried to use what is called a chi inhomogeneity to be able to do this, something called chi2. But it's very hard to get the chi2 which would implement directly a control knot. So around the year 2000, my colleague Manik Neal and Jerome Melbourne together, in fact, we were trying to prove that using photons was a useless idea. And we stumbled into this idea of inducing nonlinearity using single photon detectors. And in fact, single photon detectors, which we be able to distinguish between 0, 1, and 2 photons, and use the feedback of this measurement to induce a nonlinear gate for photons. Most people would have given up there because if you do this, the gate is non-deterministic. And so there, it means that when it fails, then it creates an error for quantum computation. If you not have known quantum error correction, then you know that this would seem to be a hopeless thing. But fortunately, Manik Neal and Gerard and I knew about error correction. And by using the idea of error correction in these single photon detectors and feedback, we were able to show that we could, in principle, build a quantum computer. Although I must admit that the amount of resources and the amount of photons that it would take was very, very large. But fortunately, very smart people started to use this idea, and kind of Jeremy O'Brien and Terry Rudolph are some of those who are using the idea of one-way quantum computation, where we build a very large initial entangled state of photons, kind of all entangled with each other. And by making a single qubit measurement, you can essentially simulate a quantum computer efficiently. And you make a single measurement, depending on the result that you get, the next measurement is done in a slightly different 1 qubit basis. And by this, you can do the same thing as a usual quantum circuit. And using these ideas have been influential to try to build a quantum computer. And I'll mention that a little bit in a few minutes. So not only we need to have this control, but we need to have single photon detectors. And this is one of the challenge in these in this implementation, is to get very good single photon detectors and something that can detect 0, 1, and 2 photons. Challenge for noise, photon loss, as we go through these fibers, temperature gradients, which implicitly assume implement some kind of Z rotation when you don't want to implement them. Photon timings, that these photons are emitted by photonic sources exactly at the time that you want and with the same waveform. So when they go through these beam splitters, that they can interfere as qubits and don't have kind of waveforms which are different and would lead to error in the 1 qubit gate. Success of photonics, demonstration of quantum computation with up to 10 qubits. Using down conversion, go from optical table to silicon chip, which has reduced the noise drastically, and use of silicon and the leverages of optics fab facilities to be able to implement chips who implement certain quantum computation. challenge is that the overhead is quite large still. I mentioned the KLM proposal, the R.Laflamme Melbourne, took an incredible amount of resources. Now, from a computer scientist, it was not exponential, so it was kind of kosher for them. But for somebody in a lab, that was overwhelming. This has been trimmed quite a lot, but there's still some improvement to be done in there. As I mentioned, relative phase and timing between photons is also a challenge, but much progress has been done. In fact, there's 2 companies that kind of are pushing, at least 2 companies I know. There might be some ones around the world, PsiQuantum in California, and to a great amazement, they raised an incredible amount of money, around $450 million, the last I heard, about to build one of these quantum computer using optics. But we have heard very little about their progress. So they're not showing where they are. And so it'll be very interesting to see in the next year or 2 or 3 to see if they are able to implement something in a robust way, which they claim they will be able to do very soon. The company in Toronto called Canada, who use not single photons but Gaussian states and some entangled, some squeeze states, and be able to build quantum computers out of this. So the next, I do apologize if you hear the dog in the background. This is part of kind of working at home and doing these Zoom conferences at home. So I'm kind of going to move to ion traps. The idea of ion trap is to use the electronic states of atoms being in a ground state or some excited states as the kind of the encoder of the qubits, and having a bunch of these atoms next to each other, and then use the center of mass. And I'll come back in a minute why this is there. So these atoms are kind of brought together in what is called an ion trap. Here, a set of 4 rods that are put together with some end caps. The end caps create a potential, which is shown here, and here I have the z-axis and that side. So harmonic potential, which is relatively shallow, and then these oscillating rods provides a confinement in the x and the z-axis, the x, sorry, and the y-axis of the strap. You would initially think that you could just put potential here, but Earnshaw's theorem tells us that we cannot have a static potential which confines electric charge. So what instead people have been doing is take some RF, RF potential, which is changing as a function of time, and the RF potential makes one of these saddle traps, and then as function of time, you change the field as a function of time. This kind of saddle is going to change, and there are some kind of miracle of technology. There is some value for which the velocity of this and the strength of these fields confine the electron in the xy direction. So once you put this in a trap, you end up with a bunch of atoms. This is the z direction, and they are confined in the x and the y direction. So the preparation of this system is set up to take the atomic levels and kind of bring them in a state, let's say 0 or 1 for each of the atoms, and also including the center of mass. So the center of mass in the x and the y direction are very stiff, so they are relatively easy to put in the ground state. A little bit more work has to be done for the one in the z direction, in this direction here or there, but this can be done by detuning these lasers and be able to take off the excitation modes that are in the center of mass. And the center of mass is going to be used to do the 2-qubit gates. Okay, so first, the 1-qubit gates are just laser pulses which go in the Hilbert space of our state 0 and 1, and depending on the phase and the length of these pulses, then we can make different types of gates, and we can show that you have a universal type of 1-qubit gate. And for the 2-qubit gates, the challenge is instead of irradiating at the frequency between the 0 and 1, we can change the frequency just a little bit. And so we can excite between the ground state and the excited state, or go from the excited state and change the center of mass mode in there. So the idea is to use these lasers to transfer the information, which say on the first atom, transfer it to the center of mass mode, and then have the center of mass mode interact with the second atom, and then make one of these CNOT gate, and then we finish the CNOT, the total CNOT gate back to the atom A1 by kind of taking the quantum information, which is the center of mass, bringing it back to the atom there. So this mode here, often called a bus mode, kind of move the quantum information from atoms to the center of mass, make them interact with any of the atom that we have desired in there, and then kind of bring it back to where it come from. That brings to something which is very interesting for ion trap. If we add in an MR something which is this form, or in optics, to make a gate between this qubit and this qubit, we would have to kind of make a swap here, swap here, swap here, swap here, make them interact, and then move on to our algorithm. But ion trap have the ability of making an interaction from here to here in one gate instead of having to do all these swap gates. Okay. The noise in the system is related to trap heating, overlap of pulses, and different phase stability of the lasers. Success of ion trap, low fundamental decoherence of these ions. So the coherence is very long, so we're very happy. So most of the decoherence that occurs is induced through the control of these systems. Instead of using these 4 rods that I've mentioned, recently microfabricated traps have been used, and so they are more precise, and they lead to, again, less decoherence due to the heating of the center of mass mode. Error for 1-qubit gates are typically of the level of 0.3 to 0.03%, and error for 2-qubit gates are a bit larger than this, 1%. And so this is work that the ion traps have to do, is to reduce this error gate in order to be one day to do full quantum error correction. The kind of largest quantum computation have here 11, but there was a paper by the group, the INQ group, last week or two, which kind of showed 13 qubits and addressable pairs. I think there were 66 instead of 55 of all these kind of different qubits being able to interact with each other and without having to go through these swaps. Program length about 60 qubits, and we'll see what it corresponds to in terms of benchmarking in a few minutes. Challenge of ion traps is the number of qubits and kind of increasing the number of qubits while not increasing the error rate. And one of the challenge that we have in there is that as we increase the number of qubits in the Z potential, which is relatively shallow, and the ions becomes kind of the control NOT gate between the ions becomes slower and slower, and then makes the quantum computation much slower. So at some point, we'll have to move to a different type of architecture and some kind of railway track architecture, where this is the usual trap that I have mentioned up to now, but you will be able to take one ion here and move it to a second one, or a third part of another kind of local trap, and be able to do quantum computation of that one. People have shown a little bit of movement of those, but it is still quite a challenge. So I have just a few minutes left, about 5 to 10 minutes. So I'll talk about superconducting qubits. You will hear more about this from John Martinez, I think later on during the week. And so I will be rather brief. The basic idea is to use these electric circuits that we've learned sometimes kind of as an undergrad, but to transform them using a superconducting material so that there will be no resistance in there, because the resistance would correspond to some form of decoherence. So we use inductance and capacitance, and a voltage source, and then we can look at what we can do. And you remember that if you have a linear inductance and a capacitance, this would lead to an harmonic oscillator. And if we have an harmonic oscillator, then the third level, the difference between the third level and the second one is the same as the second one and the first level. And so it's hard to kind of make qubits out of this. So what people have been able to do is to use Josephson junction, which is a nonlinear inductor, bringing this third level to a different frequency so that we can irradiate the first and the second level without reaching the third level. And so this has been the start of doing these superconducting qubits, really kind of systems that started by IBM in the 1980s by a researcher called Claudia Tesch, who was trying to implement ideas of Tony Leggett of making microscopic superposition of quantum systems. Got improved in the 1990s by people like Hans Moy and Nakamura and Neck in Japan, who kind of showed the first Rabi oscillation of these systems. So once we have the circuits, we can use we can cool them to about 100 to 10 to 100 millikelvin, and this temperature comes in because the frequency that people have been looking at are about 10 gigahertz. And if you take an electron at 10 gigahertz and you want its Boltzmann distribution to be mostly in the ground state, you have to go down to this temperature, and this is done by using dilution for refrigerators. In the control, we can use 1 qubit gates using microwave lines, which will kind of interact with these circuits and be able to make our qubits kind of change from one state and go around the Bloch sphere. The 2 qubit gates, there's a variety of schemes. Obvious one is your qubits is designed as to be the flux going up or going down for the state 0s and 1. The dipole-dipole interaction between two of these systems could lead to the 2 qubit gates, but more recently, focus has been done instead of using the dipole-dipole interaction to use a resonant cavity, having 1 qubit at one part of the cavity, another one at the other part of the cavity, and then use the cavity as a bus mode, not fundamentally different than what's been seen in ion trap, and induce interaction between some of these things. Interestingly, the noise there in T2 is about of the order of T1, which is the limit of what T2 can be. We've reached this, and in part a great improvement in this has been to kind of manipulate the Hamiltonian. And this is one of the great things about superconducting qubits, is that you are able to manipulate the Hamiltonian of these systems, kind of fabricating something which have slightly different properties. And one of these kind of qubit called the transmon got invented about 10, 15 years ago. And these transmons are more robust to noise than, for example, the flux qubit or what is called the charge qubit. So the transmon has led to quite a lot of progress and interaction between the qubits. Success of most advanced technologies is superconducting qubits. In my slide, I had 50 plus qubits from the Google, which has kind of demonstrated or claimed to have demonstrated quantum supremacy, or maybe we should use the word quantum advantage, as the word supremacy is getting out of favor. But last week, IBM have claimed that they have a system with 127 qubits with a 2 qubit gate error about 2%, which means they cannot kind of couple all of them in one shot without having a relatively low error rate. But the experiments by Google was able to show a computation which is just at the border of what classical computers can be able to do. Challenges of superconducting qubits still need to reduce noise, increase number of qubits, and qubits have to have different frequencies, so that's kind of challenge for calibration. But this is some kind of problems that all quantum computers will have. And so a lot of work on engineering the control and have all these lines get again a dilution refrigerator. So I'm nearly running out of time, so I'm just going to mention a few things that people have been working on kind of benchmarking quantum computers. definitely for early stage quantum computers, the benchmarking were Rabi oscillation, making the system in superposition of states, or the next step was to do state of process tomography, because Rabi oscillation gives us only a limited number of information about the quality of a device. State and process tomography tells you exactly what is happening to your device, but the scaling of those for n qubit goes like 4 to the n or 4 to the 2n. And it doesn't take you very long to realize that if n is equal to 10 or 20 qubits, the number of parameters go up incredibly fast. So we will not be able to do state and process tomography for very large quantum devices. In fact, process tomography has been done for 3 qubits nowadays, and I don't know of process tomography for more than that. State fidelity is if we know some states which have we can measure relatively easy, but then reach some certain amount of entanglement and explore quite a lot of the Hilbert space, for example, states which are related to the Clifford group that I mentioned before, then we might be able to kind of measure this fidelity in this. But interestingly, some work on what is called random benchmarking, the idea of making a bunch of gates which are part of this Clifford group that I mentioned before, like a set of a number of gates here, and we look at the fidelity of them. So we do many of these gates, and let's say here 3 of them. So we would do let's say a H1, an X gate, and then other H gates. That would be kind of one sample in here. Then you can do HHX and see kind of if the fidelity is the same. And when we finish this because these gates form a group, then we take the reverse of it, and then so we should go back to the initial state that we have, which is, let's say, 0, 0, 0, and 0, 0 here. And the discrepancy between getting 0, 0 and something else is the error rate that we have. So we make this plot for, let's say, 3 gates, and here 7 gates and 11 gate, and the slope of this corresponds to an average error per gate. Okay, and this is error per gate is the error which kind of relate to the depolarizing model. So the polarizing model is going from rho, going to 1 minus epsilon rho. The state is untouched, or it turns into the total mixed state. And so that type of model gives us an idea of one number, which gives you an idea of an error gate. And the error rates that I've mentioned in the talk are all related to randomized benchmarking. IBM has recently suggested something which is called the quantum volume, which is pretty much take a circuit with a number of n qubits and a depth, which is the number of gates that you have. Take the depth equal to the number of qubits and make the following circuit. You'll do random one qubit gates, and then you'll do a permutation, and then you'll do the same thing again. And so this makes a random circuit. And then you go and calculate if you get the right fidelity. And as long as you get a fidelity of order 1, then you will increase your number of qubits here and depth, which will increase this number here and get you an extra quantum volume. So example, I've got quantum volume that people have reached, both at IBM and Honeywell, are between 32 with about 1,000. And here, the Honeywell type of gate is advantageous, or the ion trap, as doing this permutation is relatively easy on an ion trap, but pretty hard on a superconducting qubit. And finally, the type of algorithm that we would like to have in the future is obeying, doing the Shor's algorithm, which will take quite some time, or doing some Clifford gate in the future. So I'm looking at the time, and kind of my hour is over. So just to finish, next step for quantum computing, definitely an incredible amount of progress in the last 5 to 6 years of really going to very, very small prototypes of devices which aim before about 5-6 years ago to really show that the idea of quantum computation was not crazy, that we could put superposition of many qubits together, up to a dozen of them, but really recently in the last kind of 3 to 4 years, reaching out to about 50 qubits, or to maybe 100 if the IBM device is working properly, and really start to think about implementing a quantum algorithm in there. Definitely, we still need to increase the number of qubits. We will need to implement at some point quantum error correction, where we'll need kind of many thousands of qubits in order to do this. And there are claims, and you'll probably hear John Martinez claiming in the next couple of days that that probably in 10 years from now, we'll be able to have a 1 million qubit quantum computer. And once we have there, we'll still have to work with theoretician to increase the efficiency of quantum algorithm. It's the number of gates that we need to do for kind of realistic, interesting algorithm is still quite large, and quite a lot of work needs to be done in there. And hopefully, in the coming years, we'll be able to show an improvement in a real-world problem, something that will be really, really exciting. So thank you very much, and I'm happy to answer some questions.
Thank you very much for your presentation. Let's just see if we have some questions here. All right, we have 2 questions up by Colin. The first one is, are there some crystals which can act as CNOT gates? Maybe that was in the optical circuit.
So if it is in the optical system, optical implementation, the answer is no, because having a CNOT gate is, or maybe I should be slightly more careful. So to have a CNOT gate, we need to have a nonlinear interaction between the photons. So we would have to have some crystals. We'd have a very large chi2 in terms of, for those who know optics. And this is very, very hard to do in practice. So there are values of chi2. Maybe if we make a very, very, very long crystal, then we'll be able to do this. But I think somebody at some point kind of told me that you would need a chi2 crystal, which will be kind of many kind of hundreds of meters to be able to do a control knot. So if you need many control knots in your quantum computation, then you'll have to have a quantum computer which was quite long. So we do not know. But if somebody would stumble into a device with a very large chi2, then this we would be able to implement one day.
All right, thank you. A second question by Colin as well. Why is Shor's algorithm used in benchmarking and not Grover's algorithm?
Because the gain in Shor's algorithm is exponential. The gain in Grover's algorithm is only a polynomial, a square root. And once we implement error corrections, and it'll be harder to see the improvement in Grover than Shor. But again, we could also maybe think about carefully how the Grover's algorithm is really going to help and use it as a benchmark. But I would say with Shor, it's definitely clear that if somebody takes two prime numbers, multiply them, give them to you, and these numbers have many hundreds of bits, then no classical computers can break that number. So that's a really, really good test to be able to kind of check that somebody really do have a quantum computers. I was going to suggest also some algorithms with Clifford gates. It turns out that these Clifford gates can induce quite a lot of entanglement in our systems, but they can be simulated efficiently, which is quite interesting. So you could use them to explore a good part of the Hilbert space, or the space of entangled states, which are very hard to kind of preserve when there is noise, and decoherence noise, for example. But you know what the result of the experiment is going to be. So these could be great benchmarking, but if not against somebody who tries to spoof you, because they might be able to simulate it and give you the answer of your simulation and not of what comes out of your quantum computer.
All right, thank you. Yeah, we have one question in the audience as well.
Yeah. Do you hear me? Yeah. So as a follow-up question regarding the algorithmic benchmark based on Shor algorithm, are you aware of resource evaluation that would have been made using Shor algorithm to benchmark the various approach that you presented before?
Yes. There's a paper by one of my colleagues at IQC, Matteo Marantoni and John Martinez, who calculated how many qubits and how many gates you needed to implement Shor's algorithm in a superconducting system. And the number is incredibly large. It's kind of hundreds of millions of qubits and gates. It was kind of quite scary to know this. And that's why I mentioned at the end that we have to increase the efficiency of our algorithms and find tricks to kind of reduce that, because even to something like Shor's algorithm, where kind of we know that classical computers cannot do, it takes an incredible amount of resources.
All right, thank you. Let's see, we have maybe 2 or 3 more questions. Okay, so one question by Daniel Brown. Any insider information why the stock of IonQ went up a factor of 4 in the last weeks? You're not supposed to answer that.
So if you wanted to me to give you advice, should you invest or not? I'm not going to say this because I would be worried to be sued to give a wrong advice, but there's one slide I slipped over which kind of relates on this, which I'm going to show right now, which is this this hype cycle from a consulting company called Gartner. And so they have this thing looking at different types of technologies, and they kind of have a cycle which goes from the innovation trigger, where everybody's enthusiastic that your technology is going to solve all problems in the universe. And if you read the popular press, you'll see that there is a relationship with some comments related to quantum computing. Then there's a stage which is called the peak of inflated expectation, where suddenly people realize that maybe that technology is not going to kind of solve every problem. And then there is the trough of disillusion, where suddenly that's what some people in the field call the quantum winter will be coming in here, and suddenly things starts going to move up and kind of become practical and kind of do useful things and have societal impact. And if you look at all of this, well, here's at the bottom here, we have flying autonomous vehicles. So you've probably seen, if you kind of look at some kind of advertisement on your web browser about something in Japan of some kind of flying car happening, but we're still very far from doing something which is very practical. But if you look a little bit further on, suddenly here we have quantum computing, and this little blue dot means that about the plateau will be reached in 5 to 10 years to go up there. So if you're here and you believe this thing and you believe in IonQ is really promising, so maybe you can have a little bit of leg on your investment, but you better watch out at the time where you arrive at the top, because things are going to go down. And but this is not a financial advertisement or a financial advice. No real reason except, I would say, part of hype. Interestingly, the valuation of the company of IonQ is incredible. It's like $2 billion. Investment of kind of few millions, like $600 or $700 million of people of investment. And in fact, I talked to Chris Monroe recently, and he says, "Oh, we don't have to worry about raising money for a while for our company." But you look at their recent paper, is 13 qubits, and so very humbling. And so we still have a way to do before being able to use these devices in problems that can be solved with classical computers.
Thank you. Okay, one more questions here. Are thresholds on qubit error rates for one-way quantum computing, similar to those for computation based on unitary gates?
That's a really good question. And I don't know the answer to that. But I'm sure the people at PsiQuantum know about this. And so what I'm going to do is I'm going to write down your name and I'm going to inquire. And I don't know the answer. I would have my first gut feeling is that it must be a bit worse than unitary gates, as it's more complicated to make gates in one-way quantum computing than if you do unitary. But I don't know if you can have an improvement because you do one-way. So definitely one-way simulates a unitary gate system. So there must be a relationship there. But the assumptions of when you do unitary gates, for example, that the noise is independent from qubit to qubit, as you do always measurements with the same kind of detectors, there might be some assumption also, which kind of becomes a little bit more tricky. But it's a really good question.
All right, then maybe just a last question to finish. Just wondering if you were given a universal quantum computer tomorrow, what would be the first algorithm you would run on it?
If somebody would give me one, I would, well, the first thing I would do, and when you say universal, I have as many qubits as I want, yes. I would probably do Shor's algorithm, because that one would really tell me if I have a real universal quantum computer. So again, maybe I come here, I answer this question with a little bit of skepticism of somebody giving me a universal quantum computer. So my first thing I would check to be sure that it works the way that it is supposed to work. And then I would go and do simulation of quantum physics. I would look at high temperature superconductivity Hamiltonians. Do they really predict superconductivity? There are claims, and maybe you will hear this from Christa Zvor, of problem to quantum chemistry problem to solve the nitrogen fixation problem to make fertilizers. So this is a problem which kind of takes nitrogen fixation, it's like a few % of the energy of the world. So if you can find a method a catalyst to make this more efficient, then definitely you would kind of be able to make a lot of money out of this, this new process. So I think physics simulation, chemistry simulation are the kind of things that I would look at.
All right, thank you very much for your answer. I think we reached the end of the question session. So just want to thank you very much for your talk and your contribution tonight. And for those who are following this conference, the series continues tomorrow with 2 talks. So feel free to join again with using the same link at 2 p.m. and 6 p.m. in Central Europe time. Adapt accordingly if you are in a different time zone. Once again, thank you, and have a good evening.